这个我 schedule 有点 change 哦，那就这礼拜四跟下礼拜会做这礼拜四，这礼拜四跟下礼拜应该是做第一次的 lab，那等于是礼拜四跟下礼拜四换过来这样子，然后每个下礼拜四上课，那 lab 会从这个礼拜开始。OK，好，大家要记得不要忘记。那 TA 可能之后再转一下那个 lab 注意的事项，那请大家来做一些 ASR 的实作。OK，好。Okay, and now back to the course. So we have finished question one and two for HMM, right? So now question one tells us how can we compute the total probability of a particular sequence of observation given HMM. Right? Problem two tells you if you have a model with HMM, you have you have an observational sequence. What's the best state sequence that explains that particular observation? So is that the total probability that you will see the observational sequence is the best state sequence that generates the observation that you see. Okay, so we're back to question three. Okay, now is the estimation problem. Given a model, the HMM model, you have the parameters of transition matrix. Okay, output probability, initial state probability. Okay, and then M and N. How do we estimate the model parameters to represent each specific classes? Right. Again, repeat. The HMM are used for acoustic model. The acoustic model are trained for each particular phonemes. Okay, so for each of the phonemes, it has different MFCCs and duration. That's why we use an HMM try to represent each of the phonemes. Okay, so we're trying to learn how for each of the phonemes, i.e. with all those 40 sets of phonemes, what are their HMM parameters? So in other words, how to use data observation derived from each class. The class here means phoneme class. Okay, to train your HMMs. After training or learning, you can use this train or learn model to perform recognition. Okay. So that's back to the basic. Some of these things are covered in a machine learning course. If you haven't learned it before, it's very similar to statistical based machine learning. Okay. It's basically built upon parameter estimation, right? You're using a probabilistic model to try to make probabilistic inference. Okay. So you want to estimate the parameters of those probability model given a set of observation. So again, every probabilistic model, okay, it has parameters. For example, in this Gaussian model, it has mean and variances. These are the two parameters. So how do we estimate the true parameters of a probability distribution? Okay, you can assume there's some prior distribution on data, right? So mean and the variances, for example, they originally have some prior distribution. Okay, we want to find the set of parameter within that probability distribution that maximize this probability, right? Probability of the theta given x. Okay, x is your observation. You go out for each of the class, collect a bunch of data, so that's your x. Okay, find out for all the set of parameters. For example, in Gaussian, it'll be mean. For which mean is going to maximize this probability of each of the data, each of the parameter given the observation I've seen. So that data that gives you the maximum probability will be picked as the estimated true parameter, okay, from data. Okay, we can expand this, right? This is a way to estimate what the parameters of the probability distributions are, right? So this arithmetic data of P naught hat, P of x given data, P of x. Okay, if you look at this, what's this? This is some prior beliefs on the data, right? If you assume your data is Gaussian distribution, maybe somehow you have a prior belief that the theta can only be ranges from -1 to 1, okay, with a uniform distribution. This somehow you know it, okay? Somebody give it to you. That's what we call a prior distribution. And then the probability of under that prior distribution, okay, what's the probability you see in the observation that you see, right? This is we call the data likelihood. Okay, so under a given set of mean of a Gaussian distribution, what's probably me seeing a observation that's equals to 5? Okay, if my data equals 2, we can compute that, right? So if given actual parameter you have, what's the probability? It's called data likelihood. Divided by the total probability of the observation that you see, probability of x. Okay, so basically, again, you're still trying to find the theta that maximize this function. Okay, you want to find the theta that maximize this function. Xn we do a assumption that each of the sample, right, x1, x2, x3, all the way up to xn, each of the sample are IIDs, so identical independently distributed. Okay, so that means the joint distribution of this thing becomes, product of each of the sample, a product of p of xi given data, right? So then product over n samples multiplied by your prior belief, again divided by this thing. This is just total probability theorem, right? Integrating p of x given data, p not data, d data. Okay, that's the total probability of p of x. Okay. All right, so looking at this thing, right, it means that best estimated parameter for the true parameter is the multiplication between prior knowledge of your parameter and the most likely parameter that explains observation data. Okay, so this process of estimating parameter is called statistical based method of parameter estimation. Again, repeat, keep yourself in mind, right? Any probability distribution has a parameter. Okay, Gaussian has mean and variances. Okay, we never really know the true parameters of mean and variances. We need to estimate them. How do we estimate? You go out and actually collect data. That's your observation. From observation, you can say, okay, what's the theta, right? What's the mean of that Gaussian distribution that will best explain, okay, the data that I've collected? Okay, so then those data will be the best. Okay, in this case, that's how do I find that data? You find it by saying, okay, if you have some prior belief, okay, then data should be some numbers multiplied by, what's the best data that will give me the largest data likelihood, right? Those data will be the best data, right? For example, mean of the Gaussian needs to be 3, so that this number will be largest to explain the data I've seen, compared to, say, mean equals 2, or mean equals to 1, or mean equals to 0. So you find out through that whole data space, find the data that gives me the largest data likelihood, the data that best explain parameter, the data that I have collected, multiplied by my prior beliefs on what my data is to be. Okay, so this estimation is called maximum. That is called the Bayes estimation. Okay, we'll simplify it a little bit later, but let's start here. Okay, this is a basic idea of doing statistical parameter estimation. And then as a side note, all the machine learning, statistical-based machine learning, data-driven machine learning-based stuff is based on this kind of approach. Okay. Even if neural network has parameter, the weight, okay, the biases, okay, or other probabilistic model. For example, the hidden Markov model, then you have transition probability, you have output probability. Those are parameters, initial state probability. All those are parameters you don't really know, but you want to find a set of value of those parameters that will give you the largest value of this probability function. Okay, that's a way to estimate what's the right parameter explaining the data that I've collected. Okay. So, all right, so since we know that denominator, after integration is just constant, right? So this number, right? You integrate out all the possibility data. So this actually is just a number. Okay, so finding the argmax over data, this is a number. So you actually don't need this number in terms of finding the data. So we can drop that p of x in the denominator. So finding the theta hat, okay, is just argmax of theta of this prior probability multiplied by the product of individual data likelihood or individual data sample likelihood. Okay. Now this product hard to operate as take a log. Okay, so let's push the log instead of doing product. Let's do log. So as we push the log in, this product becomes a summation. Okay, so and what we can use log is a monotonic function. Okay, so with this higher is always higher. Okay, so push that log in plus log of this product. Okay, then push this log in. Then you have argmax over theta, the log of p naught theta plus summation from I from 1 to n. These are n different samples you collected. Log of p of xi given theta. Okay. Finding the theta that's such that it maximizes this particular function. Okay, we call that maximum and posterior estimation. What's the posterior estimation? Then the most well-known is not the maximum posterior estimation. The most well-known is the maximum likelihood estimation. Okay, so the maximum likelihood estimation is this: theta hat equals to argmax theta over I from 1 to n samples of log of p of xi given theta. Looking at this term versus the term here, okay, the only thing that's different is here, right? So What that means is say if you want to do a maximum likelihood estimation, we call MLE, or maximum likelihood estimation. Basically, what that inherently tells you is that you actually have no particular prior belief on what the theta should be. Okay, so whereas if you want to estimate the parameter values for a Gaussian distribution, I really have no idea what it should be. It could be any value with any equal likelihood. Okay, then this term goes away. It doesn't matter whether you have certain belief on whether that parameter needs to be a particular value. Then this term goes away. So all the estimation will depend on what the data tells you. So what's called maximum likelihood estimation. Okay, maximum data likelihood estimation. It doesn't care whether you have a certain prior knowledge, okay, prior beliefs on whether this data needs to be a particular values or not. Okay, if they are all equally likely, or you just simply don't know, it doesn't matter. Okay, all you want to do is let the data tells you what the data should be. Then we call that kind of estimation is maximum likelihood estimation or maximum data likelihood estimation. And maximum likelihood estimation is a special case of maximum a posterior estimation by making this term goes away. Okay, so it's a special case of maximum posterior estimation. Okay, so if you do maximum likelihood estimation, look like this. It's a special case of maximum posterior estimation. Essentially, it means that you don't know or you simply don't care, okay, about the prior distributions of the parameter. You only look at the parameter and want to know what the values it should be. That explains the data you actually observe in the thing. Okay, so P of X, right? Given data, we know it's a product of n samples because they're IID or P of Xi given data. So we call this in data likelihood. Okay, X is the observation. Okay, it's basically just P of O given data, right? So it's the observation under a particular data. So the intuition should be clear. Okay, you want to find a set of parameter values for your probabilistic model such that when you compute data likelihood P of O given data, or basically boils on this number P of Xi given data, that data value, if you assign that particular number, it'll give me the largest value. Okay. And for those parameters that give me the largest value of this data likelihood, I say those are the true parameter of my probability distribution. Okay, this is very think about this, a very recursive logic here. Since we don't know what a true parameter of my probability distribution, I assume my probability distribution has some parametric form, so it relies on parameters. I don't know what the values are, so I go out and collect a bunch of data. Okay, for example, I look at a lot of R's. Okay, all these R's. Okay, I collect it. Okay, and I look at it. I want to find the data. Okay, find a parameter of my probability distribution, like data equals 1, data equals 2, data equals 3. Which of the data, as I plug in here, when I compute the data likelihood P of X given that thing, okay, whichever data give me the largest value of this function, I would say that's the true parameter for the probability distribution I have just assumed. And that's the end. Okay, then once you've done that, you finish estimation, and you finish training, and your model is learned. Okay, so even nowadays, okay, in the current age of deep learning, learning is still based on some form of maximum data likelihood estimation. You're trying to find the set of parameter of your deep learning weights such that it maximize the data likelihood function. Okay, so of course that maximization becomes very difficult. Okay, somewhat stochastic and non-controllable. So you have all the ways to try to control it. But the basic idea doesn't change. You want to find a set of parameter of your probability distribution or some functional form, such that if you want to go out collect data, pick the theta, okay, pick the values of this parameter such that when I compute this probability distribution, this data likelihood function, this data likelihood number is going to give me the largest number. So I'm picking the data that explains the best of my data. Okay. So that's why there's some people saying in a lot of these approaches, statistical approaches or data-driven approaches, data is the king, right? Because if you have very noisy and dirty data, okay, you'll find a set of data that best explains your noisy and dirty data. Okay, it doesn't mean it works well. It just means that you have find a set of parameter of those values that explain the thing you actually go out and collect. And that's why having a good quality data with a larger amount of data is very important. Okay, so to make sure this estimation is good. So when you rely on maximum likelihood estimation to estimate a parameter of your statistical model, probability model, deep learning models, largely is going to build upon this concept where the data it's going to find a set of parameters that fits the data the best, okay, and that explains the most of the data. Okay, so having this concept will continue. Let's do a very quick example. Okay, let's not start with HMH, very complicated. We'll do that later. But think about a very simple phenomena. Say you have a phenomenon that's like a exponential distribution. Okay, the amount of time the next customer will come into a store. Okay, now that's a model, right? You think that time itself, it has a probability distribution of exponential distribution. Okay, now that P of X given data, right? The time when the next customer comes into my store, or P of X given some model, and that model is exponential, just one of data, exponential minus X given data. Okay, now you don't know what the data should be, right? So I have no idea, okay, what this particular store, or store one, okay, what that distribution actually is. I cannot compute this number. I need to find out what the data should be to represent this store. Okay, so what's the best way to do? Go to that store and start collecting data. Okay, you say you collected n samples of data from that store. Okay, n samples. Now you have n samples that actually are numbers, right? 5 minutes, 6 minutes, 7 minutes, 2 minutes, 8 minutes, and you have collect n such samples. Once you have that, how do you estimate a parameter using this estimation? Okay, we can go through the exercises, right? Want to find a theta hat that's the best data, such that it maximizes this probability distribution of P of X given data. Okay, we know each of the sample I collected, I make assumption they are all independent, they are all the same, they are the same and independent, so the distribution function simply multiply. Okay, so argmax over theta, pi from 1 to n, 1 over theta, exponential minus xi over theta. Okay, pi is too difficult. Let's make sure we work in log space. So again, it becomes summation from I from 1 to n log of 1 over theta, exponential minus xi theta. Okay, now we find theta such that it maximizes P of X given theta, right? So we already know P of X, right? 1 over P of X given theta is this thing, log of 1 over theta, exponential minus xi given theta. We want to find a theta such that this thing is maximized. Want to find that this thing is maximized. So let's look at one sample at a time. Say for any particular sample, the log theta likelihood is ln, right? Log of 1 over theta exponential minus xi at that particular sample, right, by theta. Okay, now we can expand this, so that's minus x over theta minus log of theta, right? Because this product push that log in. Okay. Now, how do I find a theta such that this function is maximized or is is maximized? Okay. You take a partial derivative of this function with respect to the parameter you want to maximize. Right? So d function d theta. Okay. So then you can try to solve for it. Okay. So that equals x by theta minus 1 over n set equals 0. Now you have n such samples. Okay. This basically you just adds up n different samples of this thing. Okay. So this simply adds up. Okay. Because of know the IID assumption, so all the things just simply adds up I from 1 to n. Okay, xi divided by theta hat squared minus 1 over theta hat. Okay, we need to owe this thing. Okay, this would be set equal to 0 and solve for what the theta hat should be. Okay, so the theta hat, once you solve this function, right, this thing set it to equal to 0 and solve for theta hat. The theta hat is 1 over n, sum from x1 to n xi. Okay, so this is each individual sample you have collected at the store, right? 8 minutes, 7 minutes, 6 minutes, 5 minutes. Okay, sum up all those values, divide by n. So what you do, you take an average. Okay, the average of your data, okay, that number, okay, will be the best number you use it to compute the data likelihood of this particular store. Okay, now you have finished the estimation. Now you have this value, which is the average of the n samples value that you actually collected. Okay. Now once you finish learning, right, the system is on. The next person that comes in, okay, at a particular, you have to say you have two different stores. One store had one particular value, another store has a particular value. So if somebody tells you, okay, a customer comes in, in the next 3 minutes, okay, then you can start compute whether it's likely to come from store 1 or likely to come from store 2. Because if this number is bigger than the other number, that means this probably explains better of the observation that you give it to the model. Okay, that's at the testing phase. So training is taking the data you collected, estimating the theta that maximize that data likelihood function. Okay, once you finish estimating of that data likelihood function, you have the actual theta values. You can compute the data likelihood to a number. Okay, so you can use that way to then perform recognition or perform other probabilistic inference you want to do. So it's like this, right? You want to compute probability, but if you don't know what the data should be, you have no way to compute the actual number. So you go out, collect data, trying to find what the data should be, okay, given those data collected, so that this data equals some number. Then after that, you can start computing probability. Okay, so learning is all about finding an actual number for the parameter such that it fits a particular criterion. And the criterion is saying it'll best explains in probabilistic form the data that I've collected. Once that data is given a particular number, then you take that model to start to do probability computation. So yeah, this is a simple case of maximum likelihood estimation. Okay, you can talk about this more elaborate. This is data learning, right? This is training of your system, right? So this is the same idea. It's basically trying to find the data and maximize the likelihood function of the system. Okay, we know the basic. Okay, those are things. If you haven't taken machine learning, you probably should get some knowledge. There's a lot of that are taught in that particular foundational course. Now for HMM, right? So the same concept can still hold, right? So what we really need is try to find the theta. Okay, right now the theta is a lot, right? Because it has transition matrix, those parameters, right? You know, state 1 to state 2, what that alpha ij, what that number exactly is. You need that number to be able to compute the probability. Okay, what the output probability function is. Once you're in state 1, what's the probability that you see in a particular observation? Okay, you need a theta, okay, that actually give you a number so that you can compute it. So all those things are unknown. Okay, so what we need to do is find a set of theta values of the HMN such that this data likelihood function is the largest, right? So it's the same idea, trying to find a set of theta values within HMN so that this probably all given data is maximized. Okay, now the problem becomes tricky. Okay, because these are unknown. Okay, unknown to you, so you cannot actually compute the exact form. Okay, of your all given data. So this functional form has no closed form solution to the best parameter. Okay, because it could come from this state or it could come from that state. Each one has some probability. Okay, so there's no closed form solution to say, okay, I can directly solve the state transition equals to a particular closed form solutions. Okay, so we cannot do this maximum likelihood estimation as easy as like we do here. This particular data likelihood function, I can write it out, this d that, and I can directly set that equal to 0 and solve it. Okay, I cannot write it in this form. There's no closed form solution. We have to approximate this closed form solution. Okay, that's a problem with HMM. So the HMM for the space of ASR. So there's a very popular two-step approach for training HMMs for ASR. And then if you look into your starting at the Thursday's lab, you'll see this particular two-step approach when you're trying to run the training of HMM. Okay. One is called segmental k-means. Okay. You do a segmental k-means in a way to try to initialize parameters of HMM. Okay, because HMM needs transition matrix. Okay. You need the initial state probability, you need output emission probability. Okay, you need, under the state, if I see this observation, right, if there's a Gaussian distribution, I need to know the mean and variances and the weight, right? I need to know the initial state probability. We first use a sort of a ad hoc method to initialize that, okay? Then we use an algorithm, particular algorithm called Baum-Welch estimation, okay? Algorithm to refine these values of HMM. Okay, we'll talk briefly through, okay, each of these things. Okay, these things are first developed for ASR system. Okay, so meaning back in the 1970s and 80s when the HMMs are being introduced to automatic speech recognition system, these are the approaches that people use to train an HMM. And then people quickly realize this particular approach is a special case of a broader category of algorithm called expectation maximization. Okay, we'll talk about that as well. Okay, so it's called EM algorithm. So it's a way to actually estimate the parameters for a non-closed form solution of data likelihood function. You want to approximate that. Okay. anyway, let's start with how ASR people do it for HMM. Okay, go through the drill and we'll talk about the math behaviors. Okay, so the first step is try to find an initialization of HMM parameter using k-means and vector decoding. Then you re-estimate the HMM parameters using Bond-Walsh algorithms. Okay, so again, segmental k-means initializing parameter, Bond-Walsh will actually refine. Okay, this is an specific algorithm for HMM used in ASR. We'll talk a little bit about the generalization of this thing with a broader category called the EM algorithm. Okay, again, this training works, or this particular method works, also because of the topology, what topology means. Because of the topology that we use for HMM. Okay, again, keep this thing in mind, right? Your HMMs always have discrete hidden state. They transit between different states. When you're in this particular state, you have a probability distribution function that tells you if you're in this state, you will see this observation distribution function. If you're in this state, you see that observation function. Each of the states is going to transit with a certain probability. So those are the set of parameters we all need to estimate in this case. Okay. So the topology of HMM used for ASR, we call it left to right topology. Or left to right topology simply means okay, when in this case it's a three-state HMM. Okay, and when you say thing starts, it can only go left to right. That means when the state, you can only either stay in the same state or jump to the next state. Right? 2 can only jump to 3, or 2 stay in 2. 3 can only go to 4, or 3 stay into 3. You cannot go back to state 2. Okay, so for this kind of topology, that means things always move forward. Okay, your HMM always move forward. Okay, 1, 2, 3, 4, 5, and you finish. 1, 2, 3, 4, 5, finish, or 1, 2, 3, finish. Okay, you can only move forward. This is a special topology of hidden Markov model. But if you have a general hidden Markov model, this thing can come back and forth, back and forth. But in speech, we assume the transition always going forward. Okay, always going forward. And what that means is also that you have a right transition matrix in a particular cell, A31 equals 0. Right? You cannot have a transition actually come back to the first initial state. And so your transition matrix, okay, there are certain cells within this matrix is set to 0. You see, that HMM can only go into left to right. And the reason that is because of the speech we're going forward in time. Okay, as you speak, things move, so they hit the sound that it generates. Okay, so you're not able to come back, reshape your vocal track and resound, right? Things always just go. Once you say it out, right? So there's no going back and refixing stuff. Okay, so the system that the human speech production is originally the left to right, anyways. So the HMM topology we use for ASR is also left to right. Okay, once you have this left-right topology, we can do a very simple initialization algorithm. Okay, we call it segmental k-means. So it try to initialize the output density function. Okay, because we know for each of the state, okay, is a Gaussian mixture model. Okay, so there are n mixture. Okay, that means each of the mixture has a weight, has a mean vector, has a covariance matrix. Okay, so those are the things we are trying to initialize. Okay, so we want to try to initialize this observational density function, okay, of that Gaussian mixture model. Okay, so the idea how to do that. So again, the idea is trying to find which state goes to which feature, gather the stem state, and initialize the output distribution parameter. We call it alignment. Okay, so the step goes like this. Okay, you divide each training others, right? In speech, you go out collect speech. Okay, collect speech, and at the same time, your transcript. Okay, the written words. The transcript can be turned into phonetic transcript. Okay, so you have speech sound and also phonetic transcript. Okay, first you divide each of the training utterances that you actually know the label, which are the transcription, into n equally spaced. Okay, segments say n is the number of states in the model. So you have 5 words. Each have 5 words or 15 phonemes. Each phoneme with 3 different states. Then you split your utterance into 45 equally spaced segments. But let's just split that. So each of the words, say, take a sentence. That sentence has 5 words. Okay, it construct by 15 phonemes. Okay. So each phonemes we know we use a 3-state HMM to model that. So now we have 45 states. So basically, then we equally split this say 1 second utterance into 45 equally spaced segments. Okay. Now these equally spaced segments, okay, they're really equally spaced, meaning, first word, right, you have, say, first word, say, you have, each word, say, you have three phonemes, so each of the phoneme has three states. So a word turns into a sequence of phoneme. Each of the phonemes enter each sequence of states, okay. So the first word, first phoneme, that state, the first state takes up the 1/45 of that 1 second window of the features. Okay, so now you can look through, okay, all your training utterances, right? Because then you can look through all the training utterances, take phoneme R, the first state, look at all your training corpus, look at all the R's and their first state, look at their corresponding features. And those are features of MFCCs. Okay, then we now know, okay, all these features, okay, the features correspond to R first state are these. The features corresponding to R second state is this. Okay, the feature corresponding to R the third state corresponds to this. Okay, because you simply segment your things out, right? So in order to initialize state, then you gather those observation feature records on the J segment of your training sample called Y and J. So when this OT, if T is in a segment J of any training sample, like I said, you basically pick R first state, look through all your training utterances, look at all the R first state, their features, and pull them together. Okay. Once you pull them together, right, that's a simple idea, right? So write once, right? This is one utterance. So we have write once, so 1, 2, 3, 4, 5, 6, 7. There's 7 phonemes. Okay, so each of the phonemes you have 3 states. So you equally split this into 21 equally spaced segments. Now you have this segment, this segment, this segment, this segment, right? So this are, okay, we say we use 3-state measurement. So the first state is 1/21 segments of this thing, and here's some MSCs that you compute. Then you take all those out. You look at another utterance, maybe there's another R that happens here. The first state, take them all out. So you collect all the R first state, R second state, R third state, R fourth state. Okay. Once you collect all those things, what you do is do a k-mean clustering. Okay, because we know for each of the state, okay, of a particular acoustic model, each of the state corresponds to a Gaussian mixture model. So what that means there's a m centroid, okay, of your distribution, okay, that would each of them model as a Gaussian distribution. Okay, so you basically do another additional k-means, right? For R first state, go through all the samples, pick those things out. Okay, do a k-mean clustering. How many k you pick? It depends on the Gaussian mixture model mixture number you pick. So you say 16 mixtures, and you split into 16 clusters. If you do 4 mixtures like this, then you split it into 4 mixtures. Okay, they do a k-mean clustering. So n is the number of mixtures you decide to choose for the observational density. Okay. Then once you do this k-mean clustering, okay, each of the cluster you can compute the mean, right? You compute a mean, compute a mean, compute a mean. Okay. Each of the cluster, there are samples fitting in this cluster. You can compute the variance and compute the variance, compute the variance, compute the variance. Okay. And each of the sample, right? There are X number of samples here, X2 number of samples here, X4 number of samples here, and look at the proportion of this sample within all these things, gives you the weight of this cluster. So for each of the cluster, you can compute mean, compute covariance matrix, okay. Then you can compute the weight of this cluster. Now use these things as initialized value for a Gaussian mixture model for that state. Because Gaussian mixture model requires a weight. Each of the mixture has a Gaussian. Gaussian needs a mean and a covariance. So you assume this is one mixture, this is one mixture, this is one mixture, this is one mixture. Okay, then you take this mixture, compute the mean, becomes an initialized parameter for that mixture's mean. Take this mixture's covariance matrix, use that as a covariance matrix for that particular mixtures in that particular state's Gaussian mixture model. And then you basically have this thing. Okay. Now once you have this, you have done the first round of initialization of your parameter. Right now, right, everything, right, now you have, the segmental k-means, right, the things have been, you're going through all your utterances, maybe you have 8,000 utterances, you know the transcription, you have a dictionary, so you know how they write it as phonetic symbols. we know each of the phonemes we need a three-stage HMM to do. So we look through every utterances, split this thing into equally spaced phoneme state kind of a segments. Okay, then you go out and start collecting all through your 10,000 utterances with your corpus and say, look at the R first state, R second state, I first state, I second state, first state, second state. All those elements just deploy together. And then if I decide my Gaussian mixture model to be a 4 Gaussian mixture model, then I do k-mean clustering where k equals to 4. Once you split that into 4 clusters, then compute within cluster the mean and the variances and the number of samples falls within each of the clusters and get the weight of the Gaussian mixture model. Under that setting, now you have actually initialized the first versions of your of the output is. Okay, now what you have this, right? So the transition matrix can also be set similar because they're equally likely because you have doing an equally spaced thing. Okay, so that thing is sit there. So now what you do is you run the Viterbi algorithm. Okay, what the Viterbi algorithm is, right? Given a model, right? Given a HMM model, you have initial state probability, you have transition probability, you have a output density function, probably all these parameters set. Then you say, I want to find the best state sequence given observation, right? So you have initialized everything. Okay, then you go back and then say, okay, I'm going to use Viterbi algorithm and realign, find the best state sequence over these right ones, right? Again, now once you refining the best state sequence, okay, through the use of Viterbi algorithm, then they're no longer just equally spaced. Okay, maybe the Viterbi algorithm will realign and say, okay, these portions are all R first state. Okay, this smaller portion will be R second state. The third portion will be R fourth state because that's the best maximization probability I will find for each of the utterances here. Okay, I can do the same thing for all the utterances. Now what do you have done what we call the realignment? Okay, given a model parameter, you realign this thing to the acoustic sound. Okay, now the state will change. Okay, now recollect. Okay, now go back and look at R first state throughout my databases. Okay, because now it has changed. Okay, now I can recollect all the R first state, R second state, R third state. I can go and take, okay, T first state, T second state, and then go through all the phonemes I have in my databases, all of those things and recollect. Okay, now you can redo a segmental k-mean. Okay, then you redo it again. Okay, now you have a new set of parameter for your Gaussian mixture model for that state, for that phonemes, the weight, the means, and the variances. Okay, now you have a new set of parameter. You do it again by attribute decoding. Now you realign, okay, your training corpus using this newly estimated segmental k-means parameter. Okay. Now things can change again. Okay, the state sequence you find may not be the same state sequence as you find in the previous initialized parameters. And once you've done that, right, the R first state, okay, it may actually come from different portions of this waveform again. Now with that, then you do again segmental k-means, okay, and then you realign, okay, and then repeat these steps multiple times. Usually after a few steps, okay, you'll see that your alignment doesn't change anymore. Okay, usually 3 to 5 steps, usually the thing will stop. Okay, now you have a initial parameter set, okay, for the parameter to be used for bound watch estimation. Again, think about this, how elaborate this. This is a initialization for actual training. Okay, within the initialization, you have an initialization for initialization. Right, this is you do that initialization so that you can do segmental k-means, so that you can iterate. Once this is done, you are done initializing your parameter. Then you can start doing the actual estimation algorithm we call bound-watch estimation. Okay, but anyways, after these steps, you actually have a initial estimation, initial somewhat good estimation of each of the phonemes, their output probability function. Okay, basically the under this state, what would be my observation probably of this Gaussian mixture model, the mean, the variance, and weight. Okay. Now, once we finish segmental K-means, then we move into bound-Walsh estimation. So you may have a question, right? It seems like this seems fine, right? It's the segmental K-means, once you've done the convergence, maybe it's not too bad, right? So is segmental K-means good enough for model parameter estimation? Not really, okay. Because what's wrong here? I will talk briefly, but intuitively, what you can think about it. There's nothing we have explicitly optimized for. Everything is ad hoc. We say, okay, there's a GMM we need to initialize, so that we do K-means. Okay. By doing K-means, does that optimize anything? It doesn't optimize anything. It just gives you a number to start. Okay. Do segmental K-means, split into equally spaced, and then find the features within it and do stuff. Okay. Does that optimize the maximum direct estimation that we're trying to do? No. Okay. Because it doesn't optimize anything. It just gives you a crude starting point to do things. So it's not a very good estimation learning paradigm to actually learn a parameter, but it's a good paradigm to let you start to have a model so that you can work on. So not really. So what you can actually think about is that segmental K-means uses Viterbi algorithm with this sort of ad hoc K-means and segmental K-means method. They are not very optimal. Okay. Viterbi algorithm is a approximation procedure that follows the maximum likely estimation. It will pick out the features that are most likely that have come from a particular state, right? Think about what a Viterbi algorithm is doing, right? It is saying, okay, I want to find the state number, okay, that give me the largest probability of me seeing that observation. And you hard assign it to say, okay, R, first state is that feature, okay? Because you do Viterbi decoding, but it can be other part, maybe the other part can be, they're not most likely, but they also have some probability that you may see R second state appear in other segments of your speech. Okay, it's just not the most likely, but those probably are not going to be counted toward your estimation of R first state or R second state, okay, because of the Viterbi algorithm we use. So all those less likely feature vector are going to assign to the neighboring states, not going to be included by this particular state. And then they just ignore, okay, because you're finding the most likely state, okay, not accounting for all possible generation of that state. Okay? You only find the most likely one, okay? So they're less likely scenario where we also see our second state outputting a particular observation feature vector. All those things are completely ignored in your estimation of your algorithm. So segmental K-means using Viterbi algorithm as a way to give you a good initialization, but you underestimate the variability, the possibility that the sound each of the sound class is going to generate the feature that you see. Okay, you underestimate that the possibility of it, because it follows what we call the maximization of maximization, maximization algorithm. So it does not account for all possibility. It's not looking for most likely parameters. It's looking like, if I know this is the state, then under that state I find the most likely, but the less likely samples are not going to be counted toward the estimation of this thing, which can happen, but you will simply set it equal to 0, which may not be the right thing. Okay, so this is also not optimized for the whole probability distribution function, because it doesn't account for all possible ways you're seeing this observation. Okay, so like I said, segmental K-means tend to underestimate the amount of variability in the training data. Also, in essence, not mathematically robust. Okay, so you not necessarily want to maximize the maximum. Okay, in this case, what we really want to do, we still want to maximize some data likelihood. Okay, we want to maximize the data likelihood of the expected, okay, state sequences. Okay, Viterbi algorithm gives you the most likely one. Okay, give you that most likely one and take those features correspond to those only things that have been picked for the most likely state. Okay. But what we actually do want is, on average, okay, if this observation can come from each of these states, expected value, I want to maximize the expected value of those things. So I want to maximize the total probability of of me seeing observation coming from this state and that state as well. Okay, so we don't want to maximize the maximum. Okay, we want to maximize the expected value because the hidden states are a null. Okay, if you give it a null using Viterbi algorithm and force it to pick which samples you use the Gaussian mixture model, okay, then you're only looking at the one that maximizes the probability. If you think, okay, actually I look at every state, but I will look at all possible cases that will come into this state, but I don't know which exactly is this, so I take an expected value. I want to maximize the on average, okay, the state can take on all these features, okay, and then use those features as a way to estimate my parameter. That would be the best one. So there's an intuition behind that, okay. So initializing a parameter using this Viterbi algorithm, so if you give you a way to assume you kind of know what the state sequence is, and then you start estimating parameters. Then once you have that initial parameters, then you can start saying, okay, can I estimate something else? Okay, solution is called Baum-Marshall estimation. Okay, define a new function called FOQ lambda 2. Okay, equals to log of probability of OQ lambda 2. So for some observational sequence, O state sequence Q and lambda 2. So we can set a goal of parameter re-estimation to be maximize the expected value of the f function given a model over all possible values of q. Okay, so f o q lambda q lambda. So q, right, expected value over q. So you basically take out randomness of q. All right, so want to find the set of parameters such that the expected value of this thing is maximized. Okay. So in the Viterbi algorithm, you can imagine that process is saying, okay, I'm going to run Viterbi equally so I know what Q is. Okay, once I know the Q, I fix it to say, okay, that particular observation is that Q state. Then I try to learn the parameter that way. Okay, but that underestimate all the possibility of the Q can happen for the thing because Q itself is a random variable. Okay. The random variable is a state sequence, right? That state sequence is a random variable, so we can get the expected value over that thing and try to maximize this function instead. Not to just pick the Q that would give me the largest value of this and try to estimate the lambda. Anyway, so we can write it out, right? So expected value of that thing, right? Expected value of over Q, POQ, okay, log POQ lambda 2. Okay, we call this later on, we'll do a formal derivation. It's called expectation maximization. EM algorithm. Expectation is objective function that we try to maximize when we're trying to estimate a parameter. Okay, so given lambda is an HMN, okay, maximization of that objective function has to be iteratively. We'll talk about this later, but mostly because of the hidden nature. Okay, so the step goes from this. First, you guess a model. So the guess the model comes from the segmental k-means that you have. Then you find a new model lambda 2 that maximizes this thing. Okay, sum over all q p of OQ given lambda 1 log of p of OQ given lambda 2. Okay, so we want to find the lambda 2 such that this function is maximized. Lambda 1 is your initialized parameter. Okay, so you actually know what the values are. Okay, so you have a probability that you're trying to compute over q. Okay, that you actually know how to compute. Okay. On a function that you actually don't know, because under lambda 2 don't know, right? These are the true parameter you want to estimate. Okay, so this function, okay, trying to take the expected value over q, right? So if you look at this, right? So if people recall what the expected value function is, right? Sum over all possible x times p of x, right? So okay, imagine this is x, this is p of x, sum over all possible x, right? So q, right? So this is the x, this is that random variable. Okay. Now we look at the probability of this random variable. Sum over one of the possible cases that this entire random variable can take use the q function, right? So this is like an expected value operator of p of OQ given the current model multiplied by log of the data like new function under the true model. Okay. Then we try to do iteration of this, trying to find the local optimal of this function. Okay, the actual procedure, okay, first develop called a Baum-Marshall estimation. Okay, this is a special case of that thing. We'll talk about that computation that we're doing here. First, you get all the model parameter from segmental k-means and you do Baum-Marshall re-estimation. An estimation algorithm that refine the model parameters. Okay, now let's do things. Okay. So exactly what we're trying to estimate. We're trying to estimate is pi I, aij, and some vj and k, right? So pi I is the initial state probability. So basically, we want to find the expected number of times in state I at time t equals 1, right? As the system starts, as the HMN gets started, what's the expected number of times in state I at time t plus 1? Aij, okay, it's just the expected number of transition from state I to j divided by expected number of transition out of state I, right? So how many times I go from I to j divided by how many times I actually going out from I. Okay, that'll give you my probability of Aij, right? Now, just for simplicity for now, okay, assume it's a discrete observation, okay, b, j, okay. Under different state, you see a particular symbol k. So what you want to do is expect the number of times in state j and observing a particular symbol bk, and divide by the expected number of times in state j. Okay, so these are things we're trying to estimate. Okay, now let's try to do Baumann's estimation. Define a few terms. Okay. Recall the forward-backward algorithm that we talked about in last class. Okay. K is the training utterances. T is time. I is state. Okay. This eta t k I j. Okay. For the time. Okay. Which utterance that is? Okay. Within it, the state I and j. This would be defined as the probability of qt. At time t, you're in I state. Qt plus 1, you're in j state. Given the observation and the model parameter. What's this probability? Okay, if you rewrite them in forward and backward variables, it's basically the forward variable running up to t, okay, at the I state. You translate it from I to j, okay, and then at the j state, you have bj o t plus 1k and multiply by the backward variables and divide by total probability. Okay, so let's define this term first. Okay, eta I, ij. This is the probability that you are now in state I, you are going to state j, okay, under the entire observational sequence in this particular model. Okay. Gamma tki, right, that we write them as p of qt equals I. In the previous one, we call them bt, right? Now we call them gamma t. Okay, so this is the probability when you look at the entire observational sequence and a given current model. At time t, you're in state I. Okay, so we know that already equals to alpha t, right? The forward variable multiplied at the I state to the t, the backward variables, okay, to the t and then to the I, divided by the total. Okay, so having this in mind, let's try to give the answer first. Okay, say given a single observation O1 OT, the following expectation can be computed to refine the parameter. Pi I, we want to find the expected number of times in state I at time t equals 1. So we want to find the probability of Q1 equals to I given O and lambda, right? So you want to find in time 1, you're in state I and give me pi I. Okay, under this current model, so which is the number is gamma 1 I. Okay, so this number will be that pi I. Now, expected number of times in state I is what? It's a sum over the entire sequence t from 1 to t. Probability of qt equals I given the observation and the model, which is just sum over t from 1 to t, gamma t of I, right? So finding the expected number of times you're in state I is basically just sum over the entire sequence of frames. This variable called gamma ti, and this gamma ti is just a backward and a forward variable computed to this point. Okay, to this t and I state. Okay. BJOK is the expected number of times in state I and observing the output variable BK. Again, sum over t from 1 to t, P of QTI, OT equals VK, a particular symbol drawing from VK, basically finding all the t such that your observation equal to that symbol and sum this probability of gamma ti, right? So basically this probability, again, you're summing over the frames, but not all the frames. You're summing only over the frames that actually at that time you're in state I, and then the output probability you will see that output probability, that particular symbol, and sum it up. Okay. Aij is the expected value of transition from I to j. Again, sum from t from 1 to t, the probability of qt equals to I, probability of qt equals to j, given the model and the observational sequence, which is this eta variable, right? Sum over I from 1 to t, eta ti j. Okay. So again, repeat. You have a segmental k-means, so you actually have a version of that model. Once you have a version of the model, we're trying to compute this expected value. so that I get a new version of that model, a new version, a new values of that model. So initial state probably it has been initialized within your segmental k-means. Now, once you have segmental k-means, what you do, you can compute forward, backward variable at every utterances at every time step for all the i's and j's. Okay, once you compute all those things, you can have a new estimations of pi I by looking at pi I and say I will look at R1I. The R1I, right, gamma 1I is just this thing, right? Forward variable and backward variable divided by the total probability. Okay, for that particular utterances, and you just set time equals 1. Okay, so you have this numbers, right? That's basically for one utterances, you have this number. Now, expected number of times in state I is just looking at all this gamma ti over that particular utterances and how many times you're in the state I, okay, for all t frames. And then that gives you the expected number of times you're staying. This expected number of times you're in state J, C, and pretty simple. Okay, then you just look through an utterances, looking at all the frames. Okay, each frame you have an alpha, beta, forward, backward variable so that you can compute gamma. Okay, when you compute gamma, okay, you can look at this gamma variables, but you have another n here, so you want to make sure the frame you look at that the symbol that you're looking at is the forward symbol that you're looking for. Right? So the k symbol that happens within the particular frame and sum up all those frames gamma ti. Okay, then you have this expected number of times that you are actually in state I and see that observation. The transition, expected number of children going from I to J, is this probability. And we know this probability is just the eta ti ij. And then that probability, if you look at, it's just forward variable, backward variable. Okay, then you multiply by aij. Okay, and so bjot. This already know. Okay, because you have initialized parameter, you can compute all those things. Once you compute it again, then you have this eta kij, and you sum over that particular order, just all the frames. Okay, then you get that expected of aij. Okay, now this is for one training utterances. And so you have n training utterances. Okay, that's O1 to OT. Okay, k from 1 to k. So this whole data you can think about as a sequence of sequences of training samples. So expected values are just being expanded, right? So expected numbers of time in state I at time t equals 1, sum over all k samples, right? Sum over all k samples, you have this gamma 1 k I, okay. Expected number of times in state I, again, sum over all k samples, okay. Sum over all time, okay, within each sample, but each sample may have different length. Okay, so it's t of k, okay, because each sample can one is maybe 1 second, another maybe 0.5 second, right? Another alternate maybe 3 seconds, right? So sum over the frames, number of frames respective each of the samples, sum over all the samples. This p of qt, which is just gamma tki, right? It's just sum over all these things. So expanding to multiple orders, you just have additional summations over k orders. Repeat expected number of times. Okay, instead I observing the observation is very similar. For each utterances, you look at the sample that for those frames that actually output a particular symbol, that gamma t sum over all the samples. The expected transition transition from I to j, and you compute this eta t for the k sample I sum over t from 1 to that number of samples within that particular samples and sum over all samples you have. Then you have the expected number of I and j. Okay, right. So once you expected number of transition from I to j. Once you compute this way, you have a new number here, right? You have a new number here. Then once you have a new number here, recompute ai, alpha I, and the beta parameters. If you keep this in mind, right? If we say aij, right, it's the expected transition from I to j. Okay, this is our parameter. We use expected transition from I to j as a way to estimate this parameter. How do I find these numbers? We compute eta tij. Okay, eta tij are being computed from forward and backward variable with the transition matrix within it. Once you compute it, sum over all your training utterances, then you have a new aij. Once you have a new aij, also new bjk, okay, new pi I, okay, Then you have a new forward variable and backward variable. Once you have a new forward and backward variable, then you have a new eta. Okay. Also have a new gamma sub t, right? Once you have this thing, then you have a new variable, you have a new parameters. Once you have a new parameters, again, recompute forward and backward variables. When you have forward and backward variables again, you have new this one, new one. Okay. So this thing can iterate. Okay. As it iterates, will show that okay, there it's actually this process will continue to run and it will maximize the data likelihood function. Okay, we'll actually show that proof of this thing, okay, in a more hand wavy derivation. But by doing this iteration of this process, okay, it's gonna guarantee we're gonna find a set of parameter, okay, it's gonna always moving toward the larger and larger values of data likelihood function. Okay, so when do you stop? Okay, you stop it until when you actually don't see the data likelihood function after re-estimation. It seems like it's increasing a lot. It would always increase. Okay, because by definition this will always increase. But if the increase amount starts to plateau, becomes sort of stationary, it's increased that much, increased by 10 to the minus 6. Okay, that's very, very small. Then it's time to stop. Okay, you finish learning and you're done. So these are iterative process. Again, keep this in mind. This is we do segmental k-mean, so you have the initialized parameter. Once you have this initialized parameter, now want to look at the expected value of thing, so that using expected value of thing to re-estimate the parameters that we originally get from segmental k-means. Okay, the expected value of things are computed using basically some answers. So, but these parameters, these numbers that you see, they're actually computing from forward and backward variables. So in reality, what's happening is doing segmental k-means, so you have all this initial probability. Using all these initial probability parameters, you compute for every other state alpha and beta parameter. Alpha and beta forward and backward variables. Once you compute these forward and backward variables, you can compute this gamma and gamma sub t and also gamma sub t. Once you can compute this sum over others and sum over other frames, you have a new estimation of Aij. Then you recompute forward and backward variables. Today you have a re-estimation of this, and then you recompute. Okay, these are iterative. We call it Baum-Welch re-estimation. Okay, again, usually you'll see that also in your lab. You do sort of this re-estimation maybe a couple times. Okay, 4 or 5 times. Then you're like, okay, I'm done. Okay, then you can move on. You have at least initial working sort of ASR system. Okay, start. Okay, so again, so just always keep and repeatedly use this picture, right? So hidden Markov model, hidden state, okay. State discrete, they will transit, so there's a geometric. State will start, so there's a new state probability. For each state, there is a Gaussian mixture model that are trying to model the output probability that you see at your observational sequence. Okay. Now we take all these model for one of the phonemes. Okay, so for one phonemes, we have 3 states. Okay, so from one word, we have multiple phonemes. So in order to initialize what the parameters for these phonemes, this particular state, we use segmental k-means to begin that. Once I begin that, I try to find a lot of expectation, trying to refine 1 to 1, 1 to 2, 1 to 3, and then when you're in 1, what's the observation that you see? Okay, okay, that's concluding. Okay, so that's the Baum-Welch estimation, right? Pi I is the parameter, and repeat. This is the parameter we want to estimate. We use this particular method to estimate it. Okay, expected number of times to state I at t1 t plus 1. Aij expect number of transition from I to j divided by expected number of transition out of state active. Those are called, we call it Aij. Bj okay, now we're back to the GMM case. Okay, for each of the state, the observation is no longer discrete. It's a continuous, which is Gaussian mixture model. Okay, Gaussian mixture model is written as sum of k mixtures, right? One of the under this state, the k mixture has a weight. One of the mixture is a Gaussian distribution. Okay, for that Gaussian distribution, it has a mean vectors, right? For the state and for that mixtures, and for that mixture, it has a covariance matrix for that state and for that mixture. Okay, so for Bj of O, okay, it's this particular Gaussian distribution. We also need to estimate these things. Yeah. Okay, again, repeat. We know that expected number of times that you stay I at time t plus one is that thing. Expected number of times your state I is this thing. Okay, expect transition from I to j is this particular eta. Okay, so that eta of tk is basically the forward and backward variable computing. Gamma t of k of I, okay, is again some combinations of forward and backward variables that you compute. So really the essence about unwanted estimation is really have to be able to compute forward and backward variables. These are the actual only thing you need to compute for forward and backward variables. Okay, so now for continuous observation at GMMs, right? We know J of O is this particular summation. Let's define a new term called RTJK. Okay, that's the probability of being in state J at time t with kth measure component accounting for the observation vector like C. Right? So originally it's only RT of J, right? It's basically says the probability of state symbols, the state sequence at time t or in state J. Okay. Now you have another we call occupancy index here, right? So at time t for state J, you're in a mixture K. Okay, so that's we call the probability of that. And how do we compute that probability, right? So basically, it's a probability of you being in that state, right? The forward variable times backward variable divided by the total probability. This is just the probability of you being in that state in time. And this probability, okay, CJK, okay, of the normal distribution, right, divided by total Gaussian mixture model distribution, right? So this divided by this, right, it tells you, what's the weight, okay, of this particular Gaussian mixture within the total mixture, right? Because this is for that particular kth mixture within the state J, the weight times the Gaussian distribution divided by for all of the mixture, right, you sum it up times the Gaussian distribution. So this particular ratio tells you the weight of that particular kth mixture within the Gaussian distribution. Okay, and do you have all this number? Yes, you have all this number, right? Because you initialize using segmental k-means. So you know CJK, okay? You have versions of MJK and the covariance matrix. Okay, so you all have this in the initial state probability. So you have this gamma TJK. So the re-estimation formula, again, just give you the answer, okay? CJK is the parameter we want to estimate, which is the Gaussian mixture models for each of the state J, the mixture K, that weight is just the sum over T, right? Sum over the entire sequence. This RTJK, right? Sum over T. So again, what's left is K, right? So over JK, so this RTJK tells you the probability that you're in state J, okay, for this particular mixture. Okay, so this thing divided by sum over T, the entire length of the sequence, training utterances, sum over K from 1 to M, so there's N mixtures of this RTJK. So is this a bit particular? If you look at this, this is nothing more than a ratio between the K mixture divided by the total, right? Because here it sums up all the mixtures. Okay, so it gives a ratio between the probability that you were in that mixture divided by the probability of everything. So that gives you a estimation of the CJK, which is the GMM mixture model weight. Okay. Now MJK again can basically follow this. Okay. Sum over all T, right? Basically you sum it up, so you have this expected value. Okay. Gamma TJK, the probability that you are in this time, this state, this mixture, looking at the observation divided by the total. Okay, that gives you the weighted mean. So let's give you a sort of an average mean, okay, of this particular mixture under this particular state. Covariance matrix, very similarly, okay, finding which, okay, the probability that you're in a particular state, okay, and particular mixtures, that probability multiplied by the covariance matrix of that divided by the total. Okay, then what you get is this estimation of UJ. Okay. Now, if you recall when I first say segmental k-means, okay, underestimate the possibility. Especially look at they're missing this term, right? This term tells you the probability of a particular state, particular mixture, particular time. Okay. In Viterbi decoding, it'll give you one number. that particular state, only that state, that feature. Here it gives you a probability. Okay, you say, okay, now if you look at the state, this make sure it has this probability. It may not be the largest, but it has some probability. Okay, so those features will contribute, even if it's a low probability, you will still count. It may exist in that particular time, in that state, in that mixture, even if that probability is low. Okay, then you multiply all these things, you get a better estimate of the mean vectors of your Gaussian mixture model. And by attribute decoding, this thing is not a number, it's just yes and no. You can only have a feature correspond to one of the particular state, okay, particular time. Okay. So that underestimate the possibility of you seeing this observation. Okay, so again, these are re-estimation probability. So these are TJK, it's just a probability of you being state J at time t with the K mixture component counted per O. So the real difference between segmental k-means and then this kind of Baum-Wurst re-estimation is the Baum-Wurst estimation really looking at the probability, okay, of things, all possible ways a features will be coming from this state, this mixture at this time. By attribute decoding, will only have to initialize because it only say, okay, this feature, okay, will only come from that that state and at that time for that model. Okay, it doesn't account for the other things. Okay, and then this summing of things, right? Summing of this probability, essentially what it's doing is doing expectation. We'll show that later. So basically, it's summing of this summing of this probability gives you a somewhat of an expectation kind of thing for estimating this model parameter. Okay, so these are Baum-Wurst estimation. Again, these are answers, and if you look at the actual implementation, it's very simple. Okay, the math looks complicated. All this derivation looks complicated, but the math is very simple because all you really need, okay, is gamma TJK, and then gamma TJK only really come from this forward variable, backward variable, and this initialized segmental k-mean gives you each of the states for that particular Gaussian's weight with respect to the all the other Gaussian's weight. Okay, so you have it in your initial state probability. Once you have this, right, you compute gamma TJK. Okay, when you compute this gamma TJK, you have the observation, you have the gamma TJK. Okay, you have all these things. Run it, you get a new CJK, new JK, and then UJK. Okay, once you have this thing, what you do is go back and say, okay, now I have a new CJK, I have a new JK, I have a new UJK. I also have a new alpha and beta parameters, and recompute this. Okay, then you get a new gamma TJK. Now plug it back in here. Then you get a new set of CJK, UJK, UJK. Then repeat. Okay, then repeat. Once you repeat and repeat and repeat, okay, then you're in theory, okay, in mathematical theory, we call this expectation. It's going to maximize the data likelihood function and more and more and more. Okay, so and then at some point it'll converge. Okay, and then your parameter will be at a very good position, and then you stop. Your learning will stop, and your estimates are going to become well trained. So many mathematical notations, but what's really happening under the hood to run, say, let's write a program to do these things. The only thing you really need is to compute that forward and backward variable for each of the others and sum it up. Okay, there's some basic summation operations happening within those forward variable and backward variable. Okay. Let's talk sort of generally about this EM algorithm. We'll stop here. Okay, so we'll think about HMM again in an EM manner. Okay, so observational sequence are O. Okay, Q are the state sequence. Okay. One thing we call incomplete data likelihood is P of O given lambda. Complete data likelihood is O Q given lambda. Okay, so once I have Q and O, I actually can compute the number. Okay, when I don't know of this, I cannot get an actual complete number. I have to say I have to weight all the possibilities. Okay, okay. So but if I know the Q, okay, I don't have to weight all the possibilities. I actually do know the probability of me coming from that particular sequence, okay, of that sequence generating this observation. Now we define a Q function, okay, Q function of lambda and lambda prime, which is sum over q, okay, right? These are hidden to us, right? Hidden state, okay, hidden sequences. Log of p o q given lambda and probability of o q lambda prime. Lambda prime we call it a guess model, okay. Lambda is actually real model, the thing that we really want to estimate, okay. So we're trying to find sum over O Q, right? Q is this thing, okay. The log of this incomplete, we call complete dialectic function multiplied by the probability of OQ given lambda. So if you look at this term, like I said, this Q function is a little like an expectation operation, right? Because you can imagine this is just f of x, which is just p of x here, right? This is the p of x. Function is log of p of O Q given lambda, okay? So, and the sum over all possible cases of Q, okay? So it's finding somewhat of like out of this expected value of this thing. So we basically this Q function, okay? Incomplete dialectic is like we want to maximize. We don't know the Q, so if we do know the Q, we call it complete dialectic function. Okay, now we define a function called Q function, log of P of OQ, P of OQ lambda. Okay, now given a particular state sequence, P of OQ lambda is easy, right? P of OQ we know already, right? Initial state probability multiply T from 1 to T, A QT minus 1, QT, B QT OT, right? So every time you're going from state QT minus 1 to QT, right? And when you're in QT, you see the observation T, and you let the time roll, so T from 1 to T. Okay, so we know this thing, P of OQ given lambda. So we know Q of lambda given lambda of Q of lambda and lambda prime, right? So and probably OQ given lambda, right? So we know this particular form. It's just this. So Q of lambda is just sum over Q log of this thing, right? Times the probability of OQ lambda prime. Okay, this is a number we can compute because you already have a model. Right? This is actually a constant. This is a number you can compute. The log of that thing, right, can be written as this thing, right? The log of that is written as the parameter that we don't know, and you expand that, okay? But with the Q function is the summation of all possible Q, push the log in, okay? Now the log here multiplied by a number is some probability of that number. Sum over OQ, right? Sum over all T, because now it's the summation, product becomes a summation. Log of A QT minus 1 to QT. POQ lambda prime. Okay. Now you can look at this. Okay, it's sum over T from 1 to T. Okay, so and one more term. Okay, and one more term of this term. Okay, sum of OQ, okay, sum over OE, the log of this term. So you have this particular function, P of OQ. When you put the log in, you have a log of this thing, a log of this thing, and log of this thing. Right, this three-thing summation. Okay. Okay, so again, repeat. We're trying to maximize this function, right? Maximize this function. Which function? This function is the log of this probability weighted by my current guess of the actual probability that this function will give, right? So I want to maximize this. And I know I can write this the three different individual terms here. One term here, one term here, and one term here. Okay? And this probability is just a number. This number we already know is from your initial probability, some guess model from an initialized model. So if you want to find, okay, what's this parameter that maximize this function? Okay, what you do is take this parameter, right, and then set it equals 0 and solve. Right? If you want to find which parameter of a qt minus 1 qt will give me the largest value of this function, you can do a partial derivative with respect to this parameter and set it equals 0. You're going to find this thing that you set partial derivative with respect to this to the function and set it to 0. Okay, so you can solve one term at a time now, right? Let's do one term at a time. It's simple to optimize the parameters independently now of the three summational terms. So log, right? Sum over q from for all possible q, log of this parameter pi q naught p of q o q lambda. Okay, equals to what? Sum from 1 to n log pi I p of O q naught equals to I. Okay, given the current number of parameters, right? So this term, right, log of the parameters multiplied by an actual probability I can compute. that probability only will matters for the qt where t equals to the 0 time this thing. Okay. Now trying to find the parameter maximize this term. So we want the d e pi I of this thing. Okay, set to equal 0. The only thing we add is this thing we do a Lagrange multiplier to make sure the summation of this probability needs to be 1. Okay, so you add a Lagrange regularizer to make sure when you do this derivative, you have to find in a way that the summation is to still be 1 because they are probability. Sum over all possible states for this probability random variable needs to be 1, right? So that's just a Lagrange multiplier to ensure the probability sum to 1. So when you can do some algebra, then you can find that, okay, set equals 0 and solve where you have this pi I then equals to P of O Q naught equals to I under the guess model divided by the total probability of the observation given the guessed model. Okay. So that becomes really the counting exercise, right? Because what's the probability of O Q naught given I am going to get guess model? You have a guess model. Okay. So you have initialized your model somehow. And then you go back and look at all the observation and look at the time where it actually starts at the first state and then divide by the total probability. And that gives you the first version of pi I. Okay, so then you're done, right? It's just a counting exercise. Okay, now move on to the second, right, transition probability, right? Sum over all possible Qs, right? Sum over the frames, okay? Log a Qt minus 1 Qt, this probability, right? Okay. Now we can look at it and say, okay, that's log of aij, right? Probability of O qt equal qt minus 1 at I, and qt equals to j, right? At time t minus 1 at time t, okay? Under the current guess model. Okay, again, sum over all t, sum over all possible I and j, okay, sum over all possible I and j, okay, right? So this particular term, right? This is a parameter. This is a particular number we can compute out of the current guess model. How do I compute this? Use this probability of all qt minus 1 equals I, qt equals j under the lambda prime log of aij. Okay. Now we have to make sure, okay, because this essentially is the parameter we want to compute. Okay, so we want to take partial derivative of this function with respect to aij and set that equal to 0 with a constraint that this summation actually adds up to 1 because this probability. Okay, so adding that constraint, then you can solve for it. Okay. Once you solve for that and jump through the algebra, then you have aij then equals to sum over t from 1 to t, p of all qt minus 1 equals I, qt equals to j given a current model, divided by sum over all t p of q and qt minus 1 equals to I, right? So this aij becomes basically under the current guess model, the number of times you go from I to j, right? Sort of divided by the number of times you're actually sitting in I going to j, right? So basically, number of times you're sitting in I, okay. And then the numerator is number of times you're sitting in I going to j. And the ratio between the two becomes the estimation, best estimation for aij. And this estimation can be computed. It's already in the guess model. Once you have that first version of model, then you update this aij, and then you can again repeat using the updated aij become this guess model and can recompute this. Okay, it boils down to the same formula as we do with Gaussian estimation. Okay, the final thing was the Gaussian mixture model, like Bj of m, right? So let's define m as another vector, okay, mq11, mq22, all the way to mqt to indicate the mixture component for each state at each time, right? So one of the things you have is very similar, okay, sum over all possible state sequence, sum over all possible state within your Gaussian mixture model, sum over all the times, log of bqt ot if I know which state that's coming from, okay, also which mixture that's coming from, and the probability of all qm given lambda prime. So I know for all the mixtures, right? So I know that particular mixtures, that particular state, that particular observation under the guess model of this parameter. Okay, then we can expand it. Okay, sum over all I, sum over all m, sum over all t, log of CIL, BILT. CIL is just a weighting of a Gaussian distribution. This is just a Gaussian distribution. Okay, for each of the state I, okay, of the mixture L, right? The state I of mixture L has a weight. Okay, the state I of a mixture L of that weight. This is a Gaussian distribution. It has a mean and variance parameter. Okay, so and multiply by this thing, right? So multiply by under the guess model, the observational sequence, you're in time in I state, and then in Qt time, the state variables, the mixture variable is in alpha mixture under the current model. Okay, again, you solve using a very similar D thing. Okay, and it's equal to 0 and solve for it. Okay, what you get then is the mixture weight update. Let's look at this, right? Probability of under the current guess model, right? Qt equals I, the mixture equals to L. Okay, divided by total. Right? So basically, it's just a ratio. Okay, between at the current model at this point. Okay, what's the probability difference between now you're in state I when your mixture is L divided by now you're in state I, yes, but your mixture is total mixture. Okay, right? So complete add up all the mixture that give you the mixture weight for each of the I state. Okay, and for the L mixtures. If you look at this term, this is the same thing as previously in bound motion estimation, which is the gamma TJK. That's the same. This is the same probability there. Okay, you can derive basically using this, Q function and maximization algorithm. Okay, and then MIL again, similarly, observation multiplied by this probability under the guess model, and the model you have no parameter, and sum up all of the things, and the variance again similarly for the thing. Okay. So expanding all these things with when you have n samples, very simple because now your Q function, now you just basically you have multiple basically k from 1 to n, this product of this function. Okay, so basically you just add another summation in front of this Q function. This is the whole finding the maximum kind of derivatives still stay the same, but you have one more summation and you need to add with respect to this. So if you look at this whole process, okay, skip a little bit. If you look at this whole process, right? We started with saying, okay, we have segmental k-mean, so we're able to initialize the HMM parameters, and then we initialize. Once we initialize, we have a set of formula. Okay, we just tell you, okay, that's the formula to compute the Baum-Welch estimation. Basically, you just compute alpha, beta variables, and then those will give you the probability measures, and then those probability multiply, you get the updates for AIJ, BJK, and also pi I, and then all these things. Okay. The mathematical foundation here is basically you effectively what's doing is you're maximizing this function. Okay, so when you implement those equations, okay, you're actually maximizing this equation. Okay, this function, and this function we call the Q function, is a function telling you, okay, let's look at the true parameter. If I do know what the Q is, but I don't know, but if I do know what the Q is, I have a P of O Q lambda, and then take the log of that thing. Okay, and then multiply by my guess. Okay, I think what my current parameters are, I can compute the probability of this, how likely this thing occur, right? And then sum over all possible ways this thing will occur, right? So, and we want to find the set of parameters that this function will maximize. That's why it's called expectation maximization, right? And repeat, because the Hindenburg model, you have no idea what the state sequences are. So what you do is that if I do know, then I have a closed form solution to write out my probability of OQ and lambda. Okay. And that probability of OQ and lambda, there's a probability associated with that, right? If I see this particular sequence with this particular state sequence, there's a probability associated with that O and that Q, and that's the probability here. Okay, and the probability here, how do I compute the probability? You actually do some guess initial state initializing your parameter. You have a probability. So now I have a probability sort of multiplied by one possible way this thing can occur, and I sum over all possible ways this thing will occur with the associated probability. That's expected value, right? Expected value of a random variable, sum over possible ways a random variable can take out a value, multiply the probability of that random variable take on a particular value, right? The sum over possible ways your hidden state can take on some hidden state sequences. Okay, then multiply by the probability of that observational by that particular random variable's probability. Okay, and these two things multiply and sum it up. Okay, so and you want to find a set of parameters that maximize these Q functions. And when you solve that, it'll give you the same equation as the bound-walk estimation. So the expectation maximization algorithm, this is what it comes about. Okay. So if you have a probabilistic model, there's something that's hidden you don't know that depends probabilistically, okay, on everything else. If you assume, okay, I know it, okay, if you assume there's no longer random, it's not random, it's actually the thing I can actually see, okay. Once I know that, I just need to weight it by the probability associated with that, okay, and sum all those things up, the expected value, I maximize this, okay. There's a separate proof I don't think we have time to do, okay, is by maximizing this Q function, which is a expected value of this complete diagonal function, in the long run, okay, it's gonna converge, okay, to as though you're maximizing directly on log of P of lambda. Okay, so maximizing the expected value of this Q function, okay, which is the incomplete data likelihood, by maximizing the expected value of the incomplete data likelihood function. In the long run, it's gonna converge to maximizing this is complete data likelihood function. So by maximizing the expected value of the complete data likelihood function, okay, in the long run, it's gonna converge to maximizing the data likelihood of incomplete data likelihood function. Okay, so we really want is P of all given lambda, and find the lambda that maximize the observation. But we cannot do that directly. So what we're doing is doing an approximation. We're going to say, okay, let's guess a model. Once I guess a model, I have a way to compute the expected value of a complete data likelihood function for this model. Now I want to find a set of parameters that maximize this sort of expectation. Okay. And once I maximize this, okay, iteratively always goes to a new parameter, goes to the parameters. You continue to push the Q function up and up and up because you're finding the parameter that this function will keep increasing. Now there's a proof that once this keeps increasing, okay, it's gonna also correspond to the parameter that will increase the incomplete dialectic function. So you're not solving directly the MLE on maximum likelihood estimation on the data likelihood function. You're solving the maximization problem on the Q function, and that indirectly maximize the data likelihood function. Okay, so that's how we sort of walk around. Okay, because there's no way we can solve it directly, but you still want the data to tell you how to best solve for parameters that will give me the largest values of this hidden Markov model. Okay, so we'll stop here a little bit. Just kind of let it sink in a little bit for you. Okay, so formulas. My suggestion, well, I'll go through this again next time we meet. Okay, just to give more intuition. But when you look at this formula, just look at it from try to interpret it. Okay, don't just look at them as symbols. Okay, interpret them, right? So this tells you, right, the probability, right, that that the HMN now at the particular time you're in particular state J, and also once you're in that state J, the emission probability is a Gaussian mixture model. Gaussian mixture model is just a composition of different Gaussian distribution. So which composition that is? Okay, the probability of me in that state and which composition of that mixture. Okay, that, right, that kind of probability weighted by total and give me the weights here. Okay, that probability multiplied by the observational sequence I see within it divided by the total thing I see, it will give me an update on the mean vectors. Okay, so again, this kind of estimation take into account the probability of the features that could be partly in a particular state and in a particular mixture. Okay, and then basically you sum up all those things to get expectation maximization algorithm. Okay, that's what we call it. EM is a general algorithm. Okay, it doesn't just for HMM. As long as you have any probabilistic distribution function that have hidden thing in them, okay, then you can use EM algorithm to solve. Okay, as long as there's a function, okay, you have no way to solve it directly. You can introduce another variables. Okay, if these variables, once you know it, you know the complete pictures, then you can solve the Q function here to maximize the other function that you don't know. Okay, and then in this case, that function is the data likelihood function, and then we use this kind of complete data likelihood function of the Q function to maximize the incomplete data likelihood function. Okay, So let's stop here. We'll, let it sort of sink in, go back and read a little bit, and then we'll come back again, okay, talk through this again, and we'll see how it actually run in practice, okay. And your lab, the Caldi toolkit and those things, it's been done in like one step, right? One function call, and then everything is done. But underneath is what's doing is this very elaborate EM algorithm, and very smart. The math looks complicated, but the computation is extremely simple because all you need is the alpha beta variable, forward backward variable. That's the only thing you need to compute everything, almost everything here. So the computation is very efficient. Okay, the estimation is quick. Okay, if you write it up using the right toolbox, it's just one line call that you can do things. Okay, but I think it will be important to understand the actual math behind this whole estimation process. 好，我们今天先上到这边。